You ever get that feeling that there's a whole world happening right in front of you, one that you just can't see? Like a hidden drama unfolding in plain sight. Well, you're right. And today, we're going to pull back the curtain on it.
All right, take a look at this cup. It's just sitting there on a table. Looks perfectly still, completely calm, nothing's really happening, right? On the surface, it seems totally at rest, but is it? The truth is, that quiet little cup is at the very center of an intense, perfectly balanced struggle. A hidden battle of pushes and pulls is happening right now. So the question is, how do we make this invisible drama visible? Let's dive in. We are about to explore the unseen world of forces. This is the study of dynamics, which is really not just about how things move, but why they move the way they do. And it all starts with meeting the main characters in this story. So at its very core, a force is just a push or a pull. Simple enough. But here's the crucial part. It's what physicists call a vector. Now that's just a fancy way of saying it has both a size and a direction. And believe me, the direction is everything. Think about it. If you push down on a book with 10 newtons of force, it just gets pressed into the table. But if you push it sideways with that exact same 10 newtons, it'll go flying. Same size, different direction, completely different result. And yeah, we measure all this pushing and pulling in newtons, named after the man himself, Sir Isaac Newton. Okay, so if these forces are invisible, how on earth do we even study them? Well, physicists came up with a really clever solution. They basically developed a special language, a way to draw the invisible so we can analyze it. It's all about making a map of the forces. We've got two main tools for this. First, there's the system diagram. You can think of this like the wide-angle shot in a movie. It shows you all the objects in the scene. But the real star of the show, the one we really care about, is the free body diagram, or FBD for short. This is our close-up. It's a focused map that shows us every single force acting on just one specific object. This is our key to finally seeing that tug of war. So before we can draw our map, we need to know who the players are, right? In our day-to-day lives, there's a recurring cast of characters, a whole roster of forces that are constantly at play. So let's meet the team. First up, the headliner, the main event, the force of gravity. This is the force of attraction that exists between any two objects that have mass. Here on Earth, for our purposes, it's really simple. Gravity is a constant downward pull, straight toward the center of the planet. It's acting on you right now, it's acting on me, and it's definitely acting on that cup. All the time, no breaks. So if gravity is always pulling that cup down, why doesn't it just fall right through the table? Well, let me introduce you to the normal force. And normal here doesn't mean ordinary, it's a math term that just means perpendicular. It's the force the table exerts pushing back up on the cup at a perfect 90-degree angle to its surface. So the normal force is the hero that stops objects from just falling through things. It's gravity's opposite number in this specific tug of war. All right, so gravity can act from way across a room, from a distance. But most of the forces we think about, they involve direct contact. They're more hands-on. Like here, you can see a direct push on a table, and over on the right, a pull on a wagon. We call these contact forces, and they have their own special names in our little drama. The push is what we call an applied force. Makes sense, pretty straightforward. But the pull from that rope, that's a special kind of contact force we call tension. Tension is always a pull, and it's always directed right along the rope itself, which is a good little reminder, right? You can't push with a rope, it just goes slack. And finally, there's the force that always seems to be working against you, friction. This is the force that resists motion anytime two surfaces are in contact. If you try to slide something to the right, friction pushes back to the left. It's the universe's great resistor. And this photo is a perfect example. As this player slides into the base, what's the force that's bringing her to a stop? You got it. It's the friction between her uniform and all that dirt. It's acting in the exact opposite direction of her motion, and that's what's slowing her down. Okay, so we've met all the players: gravity, the normal force, applied force, tension, and friction. Now for the big question, how do we figure out who's actually winning the tug-of-war? To do that, we have to calculate the final tally. This final tally is called the net force. It's the sum of all the forces acting on an object, but you have to account for their directions. Pushes and pulls in opposite directions can cancel each other out. If the net force is 0, the tug-of-war is a tie, and the object's motion doesn't change. But if it's anything other than 0, well, someone's winning, and the object is going to accelerate. It'll speed up, slow down, or change direction. The net force is the bottom line. It's what really matters. And calculating it is a really straightforward 3-step process. First, you draw that free body diagram we talked about, get all your players on the field. Second, you set the rules of the game. Decide which directions you're going to call positive, like up and right. And then third, you just add up the forces in each direction to find the total. That's it. Let's go back to a super simple example, like a chair, just sitting on the floor. Let's say gravity pulls down with 36 newtons of force. The floor pushes back up with a normal force of 36 newtons. So, if we say up is the positive direction and down is negative, we have a positive 36 and a negative 36. Add them together, and what do you get? 0. The net force is 0 newtons. And that is why the chair stays put. The tug of war is a perfect tie.
Now, we've been talking about all these everyday forces, friction, tension, and so on. But here's where it gets truly mind-bending. Physicists have discovered that every single one of these forces, they're just masks. They're all just different expressions of a few deeper, truly fundamental forces that run the entire universe. So let's do a quick cosmic zoom out.
It turns out there are only 4, just 4 fundamental forces that govern everything. You already know gravity, of course. But get this, friction, tension, even the normal force, they are all just different faces of one thing, the electromagnetic force. Then, deep inside the atom, you've got the other 2, the strong nuclear force and the weak nuclear force. And that's it. That's the whole list. Everything is just some combination of these 4. And what's just staggering is how different they are in power. I mean, look at this. If we set gravity's strength to a baseline of 1, the electromagnetic force, the one that's holding that cup up, is 10 to the power of 20 times stronger. That's a 1 with 20 zeros after it. But the strong nuclear force, the glue that holds the nucleus of an atom together, it is 10 to the 38th times stronger than gravity. It's almost unimaginably powerful, but its range is microscopic. It's this delicate, almost absurd balance of forces that is the only reason anything exists at all.
So we started this whole journey with a simple cup on a table. But now you have the tools to see the invisible drama. You can see the constant pull of gravity, the steadfast push of the normal force, the friction that holds things in place. You have the language of free body diagrams. So my question to you is this. Now that you can see the invisible, what are you going to notice differently about the world around you?